For thousands of years, we've measured time by the shadow of the sun or the swing of a pendulum. For the last 50 years, the world's most perfect tick has come from the steady hum of a cesium atom. This standard, a marvel of 20th century physics, defines the very length of a second. But a new era is dawning, one so precise it makes our best atomic clocks look like antiques. Welcome to the age of the optical clock, a technology poised not just to measure time with unimaginable accuracy, but to unlock the secrets of the universe itself. These aren't just better clocks, they're entirely new scientific instruments, ready to redefine the second, and with it, our understanding of everything. Before we dive into this quantum leap, let's understand the time standard we're about to leave behind. For most of history, time was tied to the sky. The Earth's rotation gave us the day, which we divided into hours, minutes, and seconds. In 1874, the second was officially defined as 1/86,400th of an average solar day. But there was a problem. The Earth isn't a perfect clock. It wobbles and slows down. Science needed something more stable. The answer came from the atom. In 1955, Louis Essen at the UK's National Physical Laboratory built the first practical cesium atomic clock. He harnessed a fundamental property of the cesium-133 atom. When stimulated with microwaves, its electrons jump between two energy states, absorbing and emitting radiation at an incredibly stable frequency. This atomic tick was so reliable that in 1967, the world officially abandoned the astronomical second. The new definition became the duration of 9,192,631,770 periods of the radiation from that specific cesium transition. To realize this definition, scientists today use cesium fountain clocks. They take a cloud of about 100,000 cesium atoms, use lasers to cool them to near absolute zero, and then gently toss this chilled ball of atoms upwards, like a fountain, through a microwave cavity. As the atoms rise and fall under gravity, their interaction with the microwaves is extended, allowing for an incredibly precise measurement of their resonant frequency. The best of these clocks, like the NIST F2 in the United States, are accurate to within 1 second in over 100 million years. The time signals from these elite clocks are averaged to create International Atomic Time, the stable timescale that underpins our modern world, from GPS navigation to the internet. For over half a century, this has been the pinnacle of timekeeping. But a clock that is 100 times more accurate is now here. So, how do you build a better clock? The principle is surprisingly simple. You need a faster pendulum. Every clock has an oscillator that ticks, a counter to count the ticks, and a reference to keep it stable. In a cesium clock, the oscillator is a microwave generator, and its pendulum is the cesium atom, which ticks about 9.2 billion times per second. Optical clocks use the same principle, but upgrade the components. Instead of cesium atoms, they use other elements like strontium or ytterbium. And instead of microwaves, they use laser light. Light in the optical part of the spectrum oscillates hundreds of trillions of times per second. That's about 100,000 times faster than the microwaves in a cesium clock. Having a faster tick rate is like having a ruler with much finer markings. If you divide a second into trillions of parts instead of billions, you get a much higher resolution and therefore much greater precision. Some of the latest optical clocks are so precise, they would lose less than 1 second over the entire 15 billion year age of the universe. For decades, however, there was a major roadblock. While we could generate these ultra-fast light waves, our electronics were far too slow to count their oscillations directly. This was known as the frequency chain problem. The solution, which arrived in the late 1990s and won a Nobel Prize, was the optical frequency comb. A frequency comb is a special laser that acts like a set of gears for light. It produces a spectrum of light made of hundreds of thousands of perfectly, equally spaced frequencies, like the teeth of a comb. This comb provides a direct, precise link between the impossibly fast optical frequencies of the clock laser and the lower, electronically countable microwave frequencies. With the frequency comb, the final barrier fell, and the global race to build the world's best clock began. Scientists have developed two main designs for these next-generation timekeepers: trapped ion clocks and optical lattice clocks. The trapped ion clock is perhaps the purest form of an atomic clock. It uses a single, isolated atom as its reference. To build one, scientists take an atom, say of ytterbium, and strip away an electron, giving it a positive charge. This ion can then be held nearly motionless in a vacuum, trapped inside an electromagnetic cage. This isolates it from almost all outside disturbances. The ion is then laser-cooled to near absolute zero, and a highly stable clock laser is aimed at it. The laser's frequency is tuned and locked to a specific, incredibly stable energy transition within the ion. The stable frequency of this locked laser becomes the clock's heartbeat. Because the ion is so perfectly isolated, these clocks are exceptionally accurate and resistant to disturbances. However, relying on a single atom means the signal is very weak, and it can take days or weeks of measurements to reach the highest levels of precision. The second design, the optical lattice clock, takes a different approach. Instead of one ion, it uses thousands of neutral atoms, like strontium, all at once. In a lattice clock, intersecting laser beams create a standing wave of light, forming a kind of electromagnetic egg carton. This optical lattice traps thousands of individual atoms, one in each dimple of the light grid. The huge advantage here is that by averaging the measurements over all the atoms simultaneously, scientists can achieve extremely high precision very quickly. This makes optical lattice clocks the most stable clocks in existence. But there's a quantum catch. The powerful lasers used to create the lattice trap should disturb the atom's sensitive energy levels, which would ruin the clock's accuracy. The solution is a clever trick called the magic wavelength. Scientists found that for atoms like strontium, there is a specific wavelength of laser light where the disruptive effect on the two energy levels used for the clock transition is exactly the same. The energy shifts cancel each other out, and the atom behaves as if the trapping lattice isn't even there. This magic allows thousands of atoms to be used without sacrificing accuracy. Work at places like GILA, a joint institute of NIST, and the University of Colorado Boulder has pushed these clocks to the forefront, achieving mind-boggling levels of precision. This incredible precision does more than just tell time better. It transforms these clocks into powerful new sensors that can probe the universe in ways we never could before. Albert Einstein's theory of general relativity predicts that gravity warps space-time, causing what's known as gravitational time dilation. Time literally runs slower in a stronger gravitational field. A clock on the floor will tick slightly slower than a clock on a table. This effect is tiny, but optical clocks can now measure it. Researchers at GILA used their strontium lattice clock to measure this time difference across a height of just 1 millimeter. They detected that the top of their cloud of atoms was ticking at a slightly different rate than the bottom, a direct measurement of general relativity on a microscopic scale. This sensitivity opens the door to exploring the boundary where relativity and quantum mechanics might finally meet. Optical clocks are also becoming our best tools in the hunt for dark matter. Some theories suggest that dark matter could be composed of ultralight fields that cause tiny, oscillating changes in the fundamental constants of nature. The frequency of an atomic clock depends on these constants. By comparing two different types of optical clocks, say a strontium clock and an ytterbium clock, over long periods, scientists can look for these oscillations. If a dark matter field passed through the lab, it might affect the tick rate of the two clocks differently, creating a detectable signal. A global network of these clocks could act as a planet-sized telescope for dark matter. The same sensitivity to gravity can also be used for Earth science in a field called relativistic geodesy. Since a clock's tick rate is directly tied to the local gravitational potential, you can use them to measure height. An accuracy of 1 part in 10 to the 18 corresponds to a height difference of about 1 centimeter. By linking optical clocks across continents with fiber optic cables, we could create a network of sensors to map the Earth's true, irregular shape, its geoid, with centimeter-level precision. This network could monitor, in near real time, the subtle changes in the Earth's crust from volcanic activity, the melting of ice sheets, or the depletion of underground water reserves, leading to better models for predicting natural disasters. And of course, the optical clock revolution will directly impact our daily technology. GPS relies on atomic clocks and satellites to determine your position. Replacing the current clocks with optical clocks could improve GPS precision by a factor of 1,000 down to the millimeter level. This would enable truly autonomous vehicles, safer drone traffic, and incredibly precise scientific monitoring. High-frequency financial trading, which relies on microsecond timestamps, would become even faster and more secure. And future 5G and 6G communication networks, which need perfect synchronization to handle massive data flows, will be made more robust and efficient. With all this evidence, the international metrology community is now planning to redefine the SI second for the first time since 1967. The roadmap, managed by the International Bureau of Weights and Measures, tentatively targets the year 2030 for this historic change. But before that can happen, several conditions must be met. Multiple types of optical clocks using different atoms must consistently outperform the current cesium standard. The frequency ratios between these different optical clocks must be measured with extreme accuracy to ensure they all agree. This requires a global effort, comparing clocks in different labs using both fiber links and satellite techniques. And finally, these new clocks must prove they can operate reliably enough to contribute to generating international atomic time. This is already starting to happen. Significant challenges remain, of course. These systems are still incredibly complex, often occupying entire rooms. A major goal is to miniaturize the components, with the dream of creating chip-scale optical clocks that could be integrated into everyday devices. The journey from tracking shadows to counting the oscillations of light in a single, chilled atom is a testament to human ingenuity. Optical clocks represent a true paradigm shift. We are on the verge of redefining a fundamental unit of science, providing a more stable foundation for all of modern technology. These remarkable instruments allow us to see the warping of space-time on a human scale, and to listen for the whispers of dark matter. The second, a unit of time we take for granted, is about to become more powerful than ever before. This revolution isn't just about keeping better time. It's about what we will discover and build with that time. And the clock is ticking.